Sample problem 1.6. Perform the following arithmetic operations and report the results to the proper number of significant figures. And then there's a bunch of them given here. So in sample problem 1.5, we took a look at how we count sig figs. We're going to do that right here, but we're going to do arithmetic operations as well. Some of them are addition, subtraction. Some of them are multiplication or division. Okay, so here's the thing we want to do. The guiding principle behind this type of analysis is that the result of a calculation cannot be known to a resolution or to a precision that's greater than any of the measurements that you make. Meaning, suppose that I measure the mass of three different things, and I use a scale that is only good to the hundreds scale, right? So meaning this scale on the left can only measure this mass to either 100 or 200 or 300 or 400 or 500. It cannot tell 101 or 102 or even 110 or 150. It's either going to give me 100 or 200. But suppose I have another scale, and this one can measure things much more easily. It can measure, not more easily, it can measure things to tens. So it can tell the difference between 30 and 40. Now, it can't tell the difference between 30 and 33 or 30 and 35, but it can tell the difference between 30 and 40. And suppose I have a third scale that is even more precise. It can measure things down to the nearest gram. So this one could measure a difference between 1 and 2, not 1.1 and 1.2, but 1 and 2, or 3 and 4, or 3 and 6. Now, suppose I measure three different things. And on the first scale, it comes out as 400 grams. Okay, so there's some big thing that I measure, it weighs 400 grams. Now, I'm not claiming it weighs 400 grams. What I'm claiming is the scale is saying it weighs 400 grams. It might weigh 434 grams, but the scale would measure that as 400. And then I have another mass in there that weighs less, it's 50 grams. Now, again, it may not be 50 grams, right? Using the second scale, it might be 52 grams, or 53, or 54, or 48. Somewhere around 50, but we don't know if it's 50 because we use that second scale. And then suppose on the third scale, I measure something as 2 grams. Again, it might not be 2 grams. It might be 1.9 or 2.1, but it's somewhere around 2. So here's what we would say. This may not be intuitive, but if you add these together to find the total mass, and you just did the arithmetic, you would get 452 grams, right? But here's the thing. That 400 grams might have been 450 grams. So suppose it was 450. And suppose the one that was 50 was actually 55. Let's assume this one's pretty close. It's 2. What would you get? You get 507, right? That's way different than what we got over here. So what we're saying is, even though we made these measurements, we don't know how precise they are. So when we give a result, a calculation, what we do is we use the following rule. For addition and for subtraction, the result, the answer that you're calculating, has the same precision as the measurement with the least precision. Now, which of these three has the least precision? It's this one right here. That one has the least precision. It can only measure out to the nearest 100 grams. Okay? So here's what you would do. You would add the three together and then round it to the precision of the one that had the least. The least had in the hundreds, so we would round this in the hundreds. Now, when you round to the nearest hundreds, that's here, this is closer to 500 than it is to 400, so we would round it to 500 grams. That's the idea. You round it to the measurement that has the least resolution or the least precision. Okay? So using that kind of logic, let's try part A and part B. Part C, D are different, so let's just do A and B. So A is 317.5 plus 0.675. Now these are both in milliliters, so I'll put the milliliters over here. Notice how I set this up. For addition and subtraction, if you're going to do these problems, line up the decimal points like they taught you back in the, I guess it was the 5th grade for decimal points. It would have been earlier grades without decimal points. Then, step 2, just add them like a mathematician might. Okay. Then you round it, and what you do is you look for the measurement. You look for the measurement that goes the least to the right. See, this one only goes out 1 digit past the decimal point. This one goes out 3 digits past the decimal point. So which one goes the furthest to the right? The top number. So you round it to that digit right there. See, just straight down. So the number that comes after is a 7, so you round it up to a 2. Okay, so you identify which one goes the least far to the right. You understand that? The one that doesn't go as far to the right. And you round to that particular digit. So it's important that you line these up when you do this process. Unless you're really good at doing arithmetic, then you can do it in your head. But if you're learning how to do this, make sure you just line them up like that. This is true for addition or subtraction. So let's try B. B is 47.80. Minus 2.075. Again, addition subtractions is always done the same way. Just go ahead, you line up the decimal points, and then just do the arithmetic. Liters. Remember, measurements have a number and a unit. So this is a measurement. So we wouldn't say the answer is 45.72. We would say it's 45.72 liters. You have to put the unit in your answer. Now, which one goes the furthest out to the right? It's this one right here. So that means we're going to round it. We're going to round it at that digit. So 45.72. Now the number that comes after it is a 5. So that's exactly right in between. So it's really, I'll be honest with you, it's up to you how you want to round it. Generally, I would round this up. So round it up to 0.7. 725 would be rounded to 0.73. And there's your answer. Okay. Now that 0 at the top, I didn't mention it, but that is a trailing 0, right? Trailing zeros, if there's a decimal point, count as significant. So that's why we counted it. Okay, so now we're going to move on to the multiplication and division, which is part C and D and E. I think they're all, the rest of them are dealing with multiplication division. So the way we deal with multiplication division is a little bit different. So C is 13.5 grams divided by, so let me put that over here, 13.5 grams divided by 45.18 liters. Okay, now you can use your calculator for this. So 13.5 divided by 45.18. Let me just check that. 45.18, yeah. 0.2988. I'm going to write down a bunch of numbers. 0.2988 0478. Units. Grams in the top, liters in the bottom. Grams per liter. This is a density measurement. Okay, now here's the nice thing about sig figs for multiplication division. The answer, the result, has the same number of sig figs. I'm just abbreviating significant figures as sig figs, as the measurement with the least number of sig figs. Very simple. It's easier than the addition subtraction. You don't have to line anything up. So you just count sig figs. In 13.5, there's 3 sig figs, right? 1, 3, and 5. In 45.18, there's 4 sig figs. 4, 5, 1, 8. That's 4 sig figs. So your answer has the same number of sig figs as the measurement which has the least number of sig figs. Well, that's this one up here, 3. So that means we're going to round it to 3 sig figs. So here's how you do it. There's your first one. There's your second one. There's your third one. So 0.29. But here's what happens. This third one's an 8, but the number that comes after it is also an 8. 8 is 5 or greater, so it gets rounded up to 9. And then grams per liter. 0.299 grams per liter. 3 sig figs. So multiplication and division are easier in a sense than addition and subtraction in terms of analysis of sig figs. Let's try D. D is probably multiplication. D is 6.25 centimeters times 1.175 centimeters. Yep. Okay, so that's easy enough. 6.25 times 1.175. 7.34375. Now, what are the units? 2 times 2 is 2 squared. 3 times 3 is 3 squared. Centimeters times centimeters is centimeters squared. Now, multiplication division. 3 sig figs. 1, 2, 3, 4. 4 sig figs. 3 is less than 4, so 3. So that means 1, 2, 3. You look at the number that comes after the third sig fig. It's less than 5, so it just gets truncated. You just drop it. There's your 3 sig figs. Okay. And then let's take a look at E. E is 5.46 times 10 to the 2 grams. and we're going to add that to 4.991 times 10 to the 3 grams. Now here's the problem. These are written in scientific notation. You cannot add or subtract numbers together if the exponents in the powers of 10 are different. They have to be the same to add or subtract directly. So there's a couple approaches to this. Let me write this out. Really what this means is 5.46 times 100. Well, what's 5.46 times 100? It's 546, right? And then 4.991 times 10 to the 3, 10 to the 3 is 1,000. So that's really 4,991. Now they're in decimal form, you can add them. So that's one approach. So 4,991 plus 546. Notice they both go out to the ones column. So that means that the answer is going to be in the ones column. So 7, 15, and then they're grams. We're adding grams, so there would be your answer right there. So that's one approach, is just to make them both decimal. Another approach, which might be fun to try, is to get each of them with the same exponent, the same power of 10. So here's the general rule. Left is positive, right is negative. Lip is how I remember it. Left is positive. So what I'm going to do is I'm going to take 546 times 10 to the 2, and I'm going to move this to the left, one space. When I say I'm going to move it, what I mean is I'm going to move the decimal point, one space. Now, when you move to the left, when you move the decimal point to the left, you change the exponent by the number of spaces that you move the decimal point. So if I move the decimal point one space, I change the exponent by 1. So 2 becomes 3. Left is positive, meaning if I move the decimal point to the left, the exponent becomes more positive. Okay? And then if I moved it to the right, so for example, if I took 5.46 times 10 to the 2, if I moved it to the right, the exponent becomes negative, less positive, right? More negative, 10 to the 1. More negative, okay? So left is positive. So if you move the decimal point to the left, you make the exponent. So why did I move it to the left? By moving it to the left, that gives me the same exponent, 3, as we had here. If the exponents are the same, you can add and subtract them. So now we have 4.991 times 10 to the 3 grams. And now we can add to that 0.546 times 10 to the 3 grams. You have to have the exponents be the same in order to add or subtract them. When you add or subtract them, it's not going to change the exponent, it's not going to change the units. And there you go. Okay, there's our answer. 4.44, oops. Oh, I'm sorry, I subtracted them. That's what happened there. Silly me, I subtracted them. 7 13, 15, 5. 5.537 times 10 to the 3 grams. That's the same as this one. This is the same as 5.537 times 10 to the 3 grams, right? Because 5,537 is 1,000 times 5.537, and that's what thousands are, 10 to the 3. Okay, so there you go. We ran through it all. We ran through addition, subtraction. So with addition, subtraction, you got to line up the decimal points, add and subtract, round it. For multiplication, division, just count the number of sig figs in each number and then round your answer to the same sig figs as the one that has the fewest.